We are back now. So as you would recall, last time we were discussing Cayley graphs of groups. So what is given to me is a group and generating set for this group. So in the case of R4, we had taken generating set to be R and F. R, as you would remember, it was a rotation by pi by 2, and F was flipping about x-axis. And then we could see that the Cayley graph of D4 is cubic. I had put two conditions, these two conditions. So the vertices of the Cayley graph, they were points of the group, they were elements of the group, and then two elements, two nodes, two vertices of the graph were connected by an edge if either A minus B were in S or B inverse A were in S. What's the use of expressing groups in this fashion? Many applications would come, and before that, let's practice more. Let's see a few more examples. Very simple example, I would take Z6, the cyclic group of order 6. What are the elements? I'll just write them as 1, A square, A cube, A raised to the power 4, A raised to the power 5, A raised to the power 6. Well, A raised to the power 6 is identity, so better I won't write this, only first 6 elements I am going to write. This much. I could have also written this as 0, 1, 2, 3, 4, 5, these 5 symbols, and these are forming a group under addition modulo 6. So these are the remainders and addition modulo 6. So 5 plus 4 therefore is 3, because that's what happens mod 6. So what about a generating set? So the cyclic group meaning there is one element in this group which is capable of generating it entirely. So the way I have written like this, it's very clear that A is one of them. Well, I could have taken A to the power 5 as well. A to the power 5 would have been as good as A, because A to the power 5 and then A to the power 5 to the power 2, which is A to the power 10, A to the power 15, A to the power 20, and A to the power 25. That actually is same as this, because A to the power 5, A to the power 6, as you recall, is 1. So A to the power 25 is therefore just A, because A to the power 24 is identity. And now this is A square, this is A cube, A to the power 10 is A to the power 4. So all the elements are there. So A as well as A to the power 5, both the elements are generators. Is there any other generating set? Well, I would say A2 together with A3 also generates the same group. So if I take S to be equal to A square A3, or I just take it to be 2, 3, then it's a generating set for cyclic group S, cyclic group Z6. So there are two options. Let me take S to be A. Then how does the Cayley graph look like? I have 1, I have A, I have A cube, I have A raised to the power, sorry, this was A square, so this was A square, A cube, A raised to the power 4, A raised to the power 5, like this. And then do I connect A raised to the power 5 with 1? So what's the condition for connecting edges? So either A inverse B should belong to S, or B inverse A should belong to S. So if I take this to be A, this to be B, A inverse B is A, which actually belongs to, because A to the power 5 inverse 1, that is A, and that belongs to S, right? So I'll connect it back to this. So the name is quite justified, cyclic group. I have connected, say, A to A square because A inverse times A square is A, which belongs to this set. So what about some other generating set? So I take this to be generating set this time, this one, this generating set. So let's see what happens. So I have identity, and then I have A square, I have A cubed, and then back to this. And then I have, oh sorry, A square, I have A to the power 4, and then back to this. I am connecting it because A square belongs to, so here I am doing A inverse B, that's A square, which belongs to S, generating set. And now I have A cube here, and then A raised to the power 5, and then A, which is A raised to the 7, and back to this. And I'll also connect A square with A5 because A to the power minus 2 times A to the power 5, which is A cube, actually belongs to S. And similarly, I do like this. So it turns out to be, the Cayley graph turns out to be a triangle, another triangle, and all these vertices getting connected by an edge to the outer vertex. Do you know some other group of order 6? Z6 is 1. Another group is S3, which is the group of permutations of 3 elements. So with that group also, let's do some experiment. Remember this picture, and do the experiment with S3. So what is S3? Or call it D3. You want to understand it as S3, then this is group of permutations of 3 symbols you want to understand it as D3, then this is group of symmetries of trigon, an equilateral triangle. So you recall what is D3, Dn we had seen. So we have identity, we have flipping, we have rotation by this case 2 pi by 3, 120 degree, and then we have Fr, we have R square, and we have Fr square. And it's not very difficult to see that Fr is actually same as R square F, and Fr square is same as Rf. So these six elements are there. F, if you want, so here's a triangle. F, if you want, is flipping about y-axis, and R is rotation by 2 pi by 3. So what would be the Cayley graph? So I take generating set as two elements R and F. R and F generate the whole D3. So I have identity element, and then I have R, then I have R square, and then again R square will be connected to 1 because A inverse B. So R square inverse 1, which is just R. R belongs to S. So I make these connections, and then similarly I have smaller triangle here inside. So I have R, and this is F. So this is RF, and this is F. So this is F here, and here I have R square F. So the graph turns out to be like this. So you carefully look at this graph and carefully look at the graph that was there for the case of Z6. Both the graphs look same. Are these two groups same? No. These two groups are not same. One is abelian group, another is non-abelian group. So these are two different groups, but their graphs look quite similar. You see, there's a triangle outside, and then these vertices, inner vertex is connected to the outer one, and similarly for the group D3, you have same thing coming out. Is there a way to distinguish these two? Can you read from the graph somewhat? Like this is the graph of D3, and the other one is the graph of Z6. So here is a very nice way, which is you give it direction. You consider directed graphs. So you can consider directed graphs. In fact, you can also have directed colored graphs. So you can give some direction in that picture, you can also put some colors in that picture so that you have a way to understand which one is S3 and which one is abelian group of 6 order. So how do I put the graph? How do I put the direction to this graph? So I first do it for D3, for which I know generating set is F and R. What are the elements? 1. So first maybe I'll put some, so maybe I will put some vertices first, and then I am going to connect them with edges. So 1 R square, and here is my scheme. I would put this thing. So this is A, this is B. I would put arrow like this if A inverse B belongs to S. That's it. So if B inverse A belongs to S, in that case I would put so if B inverse A belongs to S, then I would put a picture like this, and if both A inverse B and B inverse A, if both of them belong to S, then I would put picture like this. Then I will give direction to this. What I can also do is I can actually color code my generators. So for each generator you have a color. So here let me just fix one color. For R I am going to have this color. For F I am going to have this color. So I am going to have colored and directed. By so the direction I would put using these conditions, and color I'll anyway put to all the generators. So how many colors are there? Say as many as number of generators. And remember, each choice of generating set gives you a different Cayley graph. Okay. So first I am going to just put the vertices. One R square and F RF R square F. So these are vertices. And how to put color and direction? So first I am going to do it for R. So 1 I would connect to R. 1 inverse R is belonging to S. Yes, it is belonging to S. And the direction is therefore this. And now I am going to put the direction like this, because R inverse times R square is R, which belongs to S. And here I am going to put a direction like this. So you have 1 R square, R cube is same as 1. Okay, what about F? F we have chosen green color. So the direction would be both sides, because F is same as F inverse. So F as well as F inverse both belong to S. Now F is there. What about this? F is here, RF is there. Do I connect them? Well, let's see. So F inverse RF. So here it's F, here is RF. So should I join them? So in order to realize whether I should join and what should be the direction, I should consider I should consider F inverse RF and RF inverse F. So what is RF inverse F? Let's see. So this is F inverse R inverse. So that's something interesting. Whenever you have two elements X and Y in a group, if you multiply these two elements in a group, take the inverse, it is actually Y inverse X inverse. And this property has a very curious name, which is called socks shoe property. Quite curious name. So using socks shoe property, I conclude that this is F inverse R inverse F, and this is F R square F. So what would it be? So I said some time ago that R square F is same as FR. So I have F and this is FR. And F square is 1. So this is just R, which actually belongs to S. And what about this? Again, this is FRF. And as I computed here, RF is same as RF is same as FR square. So this is FR square. So this is R square, which does not belong to S. So here direction should be from RF to F. Direction should be this. And similarly, if I do it for others, direction would be this, and here the direction would be this. And here RF and R. So I have R inverse RF, which is F, which belongs to S, right? So from R to RF, I will put direction like this. What about RF inverse R? I use sock shoe property. So this is F inverse R inverse R, which is F, which again belongs to S. So I have both the directions. Similarly, here also I have both the directions. So as far as directed graph of D3 is concerned, it is this. So this is colored as well as directed. So in fact, using directed colored graph, I can it's very easy for me to read relations in the group. How is that? So in order to reach this point, for example, what you do? You take R and then you take F. This green was F. Take R, F, that's all. Or you do F, R, R, F R square. So RF is same as F R square. Other relations also you can see within this. So here you see the direction of the outer triangle is like this, which is anti-clockwise, but for the inner triangle the direction is like this, which is clockwise. What about the direction? What about the directed colored graph for Z6? You have to think about it. maybe that's an exercise for you. And that will make you realize that the directed colored graphs for Z6 and directed color graph for D3, they are actually different. Quite often all these graphs are often studied as geometric objects. And we are not going to be bothered with that in this course. But to understand groups, people use geometry and the branch of mathematics which is called geometric group theory. But we are not going to talk about geometric group theory in these lectures. Let's see one more interesting graph in this discussion, which is a graph of F2. What is F2? Free group on two generators. Do you remember free groups on two generators or n generators? There are two symbols A and B, and we make words of all possible lengths out of these two alphabets. And we also put two more alphabets, A dash and B dash, and we use all four alphabets to make words. We make dictionary, and then there are some equivalent words, collection of all those words under juxtaposition, which is just back to back. We just put those two words and form a new word. That is a group operation for free groups. So how to draw the graph, Cayley graph for F2? So I take F AB, free group on two generators, AB, you're just naming them as AB. What are the relations? There are no relations. And since there are no relations, there are no circuits, there are no closed loops in the graph. So no relations means no closed loops. In the graph. How does it work? So let me take, now I am taking color coded thing. Let me take this as A and let me take this as B. So I am taking like this, and then the reverse direction I have A dash and I have B dash. Rather I would use B vertically and A horizontally, just a way to avoid relations so that they are as far as possible. So I have A, then I have B. So this is AB, this point is AB. Or I have here A inverse, and then I have here B. So this is A inverse B, A inverse B. And here again, if I take A, so if I can do A, I can do A inverse, I can also do B. or I can come back here. So like that I have, and here again I have options of going up, coming down, going right, going left. And similarly at this point also I have option of doing this, option of doing this, and option of doing this. And once we reach these points, again I have option to do this, to do this. Sorry, the horizontal, the vertical will be green. So to do this, and to do this, and to do this. And similarly here I have option to, at this point I have option to do this, or I have option to do this, I have option to do this. Be careful, be careful. Here no crossings. So eventually what do you get? It's an image which you may like to call, if you have heard of this word, fractal. It's a huge graph. It's a graph with infinitely many vertices, so many vertices. That's quite big, and you cannot see relations in this because there are no closed loops. The group is free group. What is the application? What is the use of having all these graphs, Cayley graphs? We are going to talk about all this in coming lectures. One very interesting application would come in understanding puzzles, in understanding Rubik's Cube. In fact, whenever there is a group action, you can construct a graph out of it. And some more graphs we are going to draw in coming lectures, and lots of those graphs are going to come from symmetry. We are going to understand symmetric groups of symmetries of various geometric objects, various things like this. Do you recognize what it is? Every side of this is a triangle, and then there are 1, 2, 3, 4 vertices. It's quite familiar. I guess you saw it in your chemistry course. It's tetrahedron. Tetra stands for 4, hedron stands for number of faces. It has 4 faces. So tetrahedron, we are going to understand symmetries of this. As I told, symmetry is going to be one of the important aspects of this course. So symmetry is what we are going to understand, and we can try to write a Cayley graph of this. We can try to write the colorful directed graph of this, and all the action, all the movements of this we can understand through the movements on the graph. So to know more about these things, this is just one example of what are called platonic solids. So to understand all this, keep watching. I'll see you next time.